Okay, we are going to continue our discussion of electric potential with this here lecture. So let's review a little bit about what we talked about last time. So if you remember, initially I reintroduced the concept of potential energy from Physics 1250, and we kind of wrapped our minds around what does potential energy mean? What does it mean if the potential energy is increasing? And what that essentially means is that if the potential energy is increasing, that means we're doing something in the system that we should be able to get energy out of it later. So the classic example is if we're raising the height of some object, we're increasing its gravitational potential energy. If the change in potential energy is negative, which is a little bit abstract, but that means that we've taken that potential energy and we've converted it into something else. So that might be converting it into kinetic energy. It might be converting it into chemical energy if you're rolling down a mountain and using regenerative braking to convert that motion into electrical potential energy, something like that, chemical potential energy. Anyway, so this usually involves converting that energy to something else. So that's what we reviewed. Now, we talked a little bit about how the spirit of electric potential is sort of in the same category as electric fields, in which we are aware that unlike gravity, there are things that have positive and negative charges. So gravity sucks. Mass is always positive, right? But with electric forces, things attract and repel. And what we want to do is, instead of creating, if you remember from electric fields, instead of creating one map for the positive charged particles and another map for the negative charged particles that had all the arrows in the opposite direction, we just created this concept of electric field. So we can make one map and make one rule for the map, which is that the direction of the electric field points in the direction of the force on a positive charge, and the force on a negative charge would be in the opposite direction. So with electric potential, what we're trying to do is we're trying to make a map not of the electric fields, but we're trying to make a map related to how much potential energy is there. But we want to make this map in such a way that it applies to both positive and negative charge. And so it turns out the best way to do this is to take this potential energy and divide by Q, which is the mass of whatever charge that you're, if I have a charge Q here, what's that potential energy? The charge Q here is at the point wherever you're wanting to know what the electric potential is. And again, the electric potential does not have any directionality to it, for the same reason that when you go to the gas station, you don't buy gasoline to go north and a different kind of gasoline to go south. Energy is energy. There's no directionality to it. Likewise, there's no directionality to electric potential. And if you remember the worksheet that we did last time, the calculation for electric potential was much simpler than it was the electric field. And the reason is because you don't have to worry about the dimensionality of it. So there you go. All right. Now, when we talked about uniform electric fields, we talked about how the potential difference is the electric field times the distance. So for example, two charged plates, one positive, one negative. The potential difference is the electric field times the distance, and the programming lab has a nice time, changing the electric field and changing the distance, and seeing, in fact, that you get basically the same velocity out of that situation if you're accelerating a particle. That's in a situation where you're accelerating the particle, linearly along the axis. If for some reason that particle is moving at an angle, well then, and this distance is along that angle, well, you have to throw in a cosine theta in there, because you're traveling both parallel and perpendicular to the field lines. And if you happen to be traveling perpendicular to the field lines, purely perpendicular, well then that angle is 90 degrees, cosine of 90 is 0, and the change in electric potential is 0. Another thing we talked about is that inside of a conductor, the electric field is 0, and because the electric field is the derivative of the potential, that means that if the electric field is 0, that means the potential could be 0, but at the very least it has to be a constant, right? So any constant, the derivative of a constant gives you 0, so the potential is a constant. The constant could be 0, but it could also be positive or negative as well. And so we talked about these sorts of things. And don't forget the part at the end where I talked about what's the electric potential sort of inside of a metal sphere, and how that does not go to 0 at the center, even though the electric field is 0 on the inside. All right. So here's an interesting question. So let's say you have a battery. There's some number of volts here, and connected to these two charged plates. And so this is the positive end of the battery. So this battery sucks in electrons until this plate is positively charged, and then this end of the battery shoves negative charges onto this plate until it can't, and you end up with positive and negative plate. What does the potential energy, what does the electric potential versus position look like? So if we were in the classroom and you guys were in actual groups, we would do something like this. I would ask you which one to choose. The answer is, I believe it's this one, like that. And the reason is that if you think about, if you put a positive charge here and you want to know what the potential energy is, if you put a positive charge right next to this positive plate, then you let it go, it's going to go off to very high speed. And so the potential energy of a positive charge right over here is pretty big, right? But if you put a positive charge right next to this to the negative plate, it's going to get accelerated, but it's not going to go very far, right? So so the potential energy, in other words, the energy that you could potentially extract from the system in the form of the kinetic energy of the proton is not so much. And so you end up with a graph that sort of looks like this. And part of the reason why it looks like this is because it's the electric field times the distance. There's a minus sign, which is, so it's decreasing. The further you go to this end of the further you go to this plate, the more the potential difference is. In other words, this D it's linear with D, essentially. All right. A lot of you at this point maybe have already started the charge repulsion activity. I think this is a really fun and clever thing, but then again, I made it, so that's kind of my bias. But the idea is you're trying to program it to do something like this. And so the object is, this charge is coming in, and if I can reset this thing, it's coming in, it's repelling, and then at some point it turns around and goes back the opposite way. So we're going to talk a lot about this problem in today's lecture. And an interesting question to ask is, how much energy does it take to bring this charge all the way out from a very far distance away up to some distance to this other thing? Just for fun, let's think about what this other thing could be. So let's say that this other thing is a deuteron, and a deuteron is an isotope of hydrogen. And if you've ever heard of heavy water is not H2O, it's D2O. And so instead of having two hydrogens connected to the oxygen atom, instead you have those hydrogens have an extra neutron in the nucleus. And so as a result, heavy water is almost exactly like regular water, except it's just a little bit heavier because it has these extra neutrons attached to those protons in the hydrogen, basically. So let's imagine that this is stuck here, and we're trying to bring this other thing in here. I mean, I don't know exactly how you would hold this down, but let's say that you did. We're trying to, through a series of shoves and nudges, trying to get this thing all the way up to this spot. We want to figure out how much energy that takes. Before we do that, a fun question to ask is that if these things fuse together, and part of the reason why we're doing this calculation is to try to figure out, if we were going to try to get these things to fuse together, how much energy would it take for this proton to hit this other thing? Here's a fun question. If these things fuse together to make this, what element is that? So if you're in groups, I would ask you to answer that question. Let me walk you through it. So this thing has two protons, so the atomic number is 2. On the periodic table, things that have atomic number 2 are helium, but there's only 3 nucleons here, right? So there's 2 protons and a neutron, and so instead of being helium-4, this is actually helium-3. Helium-4, which is the most common form of helium, is the one that has 2 neutrons and 2 protons. Anyway, so they fuse together to make helium-3. There you go. It's a fun little bit of trivia. Let's treat this as stationary. I mean, it's more massive, so it's gonna, in the event that this thing was coming up close to it, this would accelerate less. Let's just imagine that it's stuck here and see how much energy it takes to sort of bring this thing out from very far away. Okay, and our goal is to try to get it within 1 femtometer. Trivia night. What's a femto? A femto is 10 to the minus 15. It's very small. And if we can get it within 1 femtometer, then it's likely to fuse. If we can't get it into 1 femtometer, it's not super likely to fuse. Long story short. So that's what we're going to try to do. Alright, so here we go. So from far away, we're going to nudge this thing. I can't, my headphones don't let me go over there, so we're going to nudge this thing, and nudge this thing, and nudge this thing. And the idea is that every time we do this, we are applying a force over some distance, right? Force times distance is the work, and so there's a variety of, so we're applying work to the system in a number of these little nudges. And so we can write this in sort of a fancy way. We can say, well, the sum of all the work for all the nudges is going to be that, which is the force times the distance. Well, the force is the electric, the charge times the electric field produced by this deuteron, right? And then the distance, the force times the distance of each nudge is going to be this delta r, the distance over which the thing moves every time that we nudge it like this. Now this electric field depends on the distance between the charges. So it's not just a constant like it was maybe last lecture. But now it actually depends on the distance, and so we have to factor that into there. So we can kind of rewrite this thing like this. And sub that in. Well, we know what the electric field is. That's kq over r squared, right? In this case, the charges of the thing are the same, so we can just leave it as kq squared. But in general, we might need to keep track of these two charges, right? Because they might not be the same. And so this is what we end up getting. So now we're going to do. Sometimes I joke that you sort of have to avert your eyes a little bit and just sort of like stare into the page. You squint, and so if you stare intently at this equation and think intently about the world, boom, it becomes an integral, like so, right? So you take the constants out of it, right? You take the constants out of the sum, and then in the limit that of many nudges, in which case the distance of each nudge that it moves is very small. You end up with something with like this integral. The integral of 1 over r squared is, if you look that up, it's 1 over r. And the limits are basically from very far away, so let's say infinity, up to femtometer, right? Because that's how close you have to get these two things. And so 1 over infinity is 0. I hope you would agree. It all works out to be this. So if you can just get that proton, the incoming proton, to have 2.3 times 10 to the minus 13 joules of kinetic energy, or if you could do that much work on it, then you can get it right up to that other thing, and hopefully the two will fuse. So not a ton of energy in the whole scheme of things, but the problem is that if you're going to do this, you want to do this a lot, So in any case, protons are very small, and so it's overall a fairly small amount of energy to get it to fuse. But just getting one to fuse is only part of the battle. Anyway, this is what the number that we get. So let's say instead, and this is related to the programming lab, let's say instead I give you a velocity and I wanted you to figure out how close these two approach. How would you go about that? Well, the key thing to realize is that energy is conserved. So in a minute I'll show you what the equation for energy conservation looks like. The first step is that you need to know what the charge of the particles are. And I think I actually do make you memorize this list, which is not that long of a list. Basically, any particle, the charge of it is the atomic number from the periodic table. I will provide you with the periodic table, so don't feel too bad about sort of forcing you to memorize these things. But these things all have the elementary charge, right? Helium has twice that because there's 2 protons in the middle. Sometimes helium nuclei are called alpha particles. That's helium-4. So there'll be, I might do a question on alpha particle. Anyway, so this is what that looks like. And then what is the mass? Well, an AMU stands for atomic mass unit. Basically, for my purposes, a proton weighs about as much as a neutron. They both roughly weigh 1.67 times 10 to the minus 27. If you get a PhD in nuclear physics, you'll find that they have ever so slightly different masses. But for my purposes, it's fine. And so a proton weighs exactly 1 atomic mass unit. A deuteron is a proton and neutron, so it weighs 2 atomic mass units. Tritium, which is an ingredient in hydrogen weapons, and hydrogen bombs, is actually 1 proton and 2 neutrons, and so its atomic mass is 3. And then helium nuclei, helium-4 nuclei, or 4. And any other nucleus is the atomic mass unit from the periodic table, which is the number on the bottom, not on the top. The larger number, if you will. So that's another part that you got to figure out. And so if I give you a velocity at which this particle is coming in, you need to calculate what the energy is. And you're going to use energy conservation here, right? So the initial kinetic plus the initial potential equals the final kinetic plus the final potential again. And I could even add equals a constant, right? Because this is all these numbers added up together end up staying the same. And so the potential energy initial is something like this. So I can't remember if I introduced this in an earlier lecture or not. Q1, Q2 over the distance between those two. If the 2 particles start from very far away, you can treat this as being infinity and treat it as 0. In the programming lab, you actually can't do that because they start a little bit too, they start unit 500 apart. So 500 and infinity, infinity is much bigger than 500. So you might not want to neglect this in the programming lab when you're doing it. But in any case, for our purposes, just for simplicity, let's set that to 0. And the kinetic energy final, well, the thing you got to realize, if this thing is coming in, I guess let me do it this way. If this particle is coming in and it's going to come to a stop and then turn back around, the distance of closest approach is that moment where it stops. And so at the moment that it stops, that's where the velocity would be 0. And so you can get rid of this thing. And so basically what happens is that this particle that comes in, it takes all that kinetic energy, converts it into potential energy, so the kinetic energy is 0, and then it turns around and does the opposite. It takes all that potential energy, converts it back into kinetic. So the point at closest approach is this, and so if I give you the velocity here, and you can figure out the mass, and the charges, you can solve for what this final distance is. And that's basically what you're going to do on the worksheet for today. Okay. So there we go. Now one interesting thing, speaking of electric potential, is that, alright, so we decided that we needed to give a proton 2.3 times 10 to the minus 13 joules, a single proton, in order to fuse with this other particle. So an important question is, how many volts of electric potential would that involve? Well, if this is our potential energy, we can divide that by the charge of the thing that we're playing around with. So we divide this by this, we end up with something like 1.44 times 10 to the 6 volts. So the question is this a human achievable volt? Is this possible? Or is this like just nuts? The answer is that there are devices that actually that can produce this. So for example, hospitals will often have, so 10 to the 6, by the way, is how many, what's the prefix on that? Milli, kilo, giga, whatever. Think about it. This would be mega. So this is about 1 megavolt of electric potential. Hospitals often have machines that go up to 10 megavolts. So when they're doing radiography for cancers or I guess some imaging, I guess. But they have devices that can do this. And so just getting a proton to fuse with another particle, that's quite possible. What's much harder is trying to get a lot of protons to fuse with a lot of particles. But at least in principle, on paper, or using conventional devices, it's possible. Okay. So actually, over the summer, I should say, over the summer, I had a kidney stone, and I've noticed in the past, like when I go to the dentist, they use I think it's 5 kilovolts potential to do X-ray imaging for the dentist. I believe when I went in to get X-rayed for kidney stone purposes, it was much more. It was like 50 kilovolts. But if they were trying to treat a tumor or something like that, that's when they kick up the voltage, because they need the radiation to be more deadly, essentially, and penetrating. All right. End of digression. All right. So last time we talked about this equation. So the change of potential between two charged plates is minus ED. And then later I said that this equation is a more generally correct equation, and how this is related to, because it's a dot product, it's related to that cosine theta thing that's there. So we talked about this last time. Both of these equations refer to situations where the electric field is constant. That it's, so this equation, if you ever apply this equation to something like, these charged particles coming together, you're going to get the answer wrong, because these charged particles do not have a uniform electric field. They have an electric field that depends like this, 1 over r squared. So don't ever use this delta V equals ED thing on charged particles. You only want to use that when we're talking about charged plates, or maybe capacitors, which we'll talk about later. So anyway, we talked about this. Now what I want to do is I want to give you an even more general equation that works whether we're talking about charged particles, whether we're talking about charged plates. And that is this thing. And so the change in potential is the integral over the electric field times this S thing. This is actually some distance. So a lot of times when you have some path that you're following, in math, calculus 3 type math, they use the symbol S to indicate that distance. You still have the minus sign here, right? So the minus sign's still there. We have the electric field. We have a distance involved, so the units are the same. And so how do we go from this to this? Well, if the electric field is constant, then it comes out of the integral. If you integrate over this thing, you just end up getting the distance. So that's how you get this from that, right? But if the electric field does depend on distance, right? So kq over r squared, 1 over r squared gives you 1 over r, and that ultimately is how you get something like this, kq over r. So this equation is ultimately where this comes from. Okay. Now in general, so that's just for one charge, right? But you could have multiple charges, and so the fancy way of representing that would be like this. It's the potential from a bunch of point charges. So where, the charge number is I, and you go from 1 to the number of charges that you have. So just as an example between this is a situation with 2 charges, and let's say you want to know what the electric potential is right in the middle of this thing. Because it's kind of like asking, like, if I had a positive charge here, how much energy could I get out of this situation, right? If I was able to put a positive charge here, and there's a proton here and a proton here, and I held these protons fixed, right? But then I let this one go and I let it accelerate, how much energy could I get from that? Well, to figure that out, we can try to calculate what the electric potential is, and maybe once we have the electric potential, we can multiply it by the charge to get that potential energy. But first we've got to figure out the electric potential, right? And so to do that, we can use our formula for what the electric potential is. And so this crazy little symbol just means a sum, so this thing just breaks down into these 2 charges. Here they're both protons, so Q1 equals Q2. So you can just sort of take that out front. And then we are, R1 from this thing and R1 from this thing. So R1 and R2 both equal 0.5 nanometers. And then we can multiply these things out. 1 nanometer is 10 to the minus 9, by the way. And so when we do the math on this, we end up with something like 5.75 volts. So that times the charge of the proton gives you how much energy that is, or you could say that it's 5.75 electron volts of energy that you can get out of that situation. Anyway, it's just like that. If you had a third charge, we just add another, plus K3 over R3. So pretty simple, relatively simple calculation. Again, there's no vectors in this. Like, just because there's a crazy looking math symbol in here doesn't mean that there's any vectors in it. So the main challenge in these problems is just sometimes calculating R1 and R2 involves a little bit of trigonometry. But that, again, that does not mean that this has anything to do with vectors. There's no directionality to this. Energy does not have directionality to it. All right. Now here is another way that you might see this expression, which when I saw this, when I was in your shoes, this scared me greatly. I'm not going to provide an exclamation for you. This was scary to me because I can sort of wrap my mind around, I can kind of wrap my mind around, integrating over a distance, right? I mean, most of the integrals in calculus are over distances, right? Maybe integrating over time, I can deal with that. But here we're integrating over like an element of charge. So my advice here is that if you ever see this, and for example, when we talk about it in the book, immediately change it to something less scary. So for example, if you see this, you can change it to something like this, which is the charge per unit volume times integrating over these three different directions, x, y, and z. So charge per unit volume times essentially a volume. Or you can change this to the charge per unit area times the area and integrate over the area. Or you can change this to the charge per unit length times the length that's there. So again, immediately convert this to something less scary. So here we're integrating over volume, here we're integrating over an area, here we're integrating over a line. Yeah, so you might see something like that in the book there. So again, that's what we get from point charge. Now, an important thing to note is that, even though I've been saying that it's only electric potential differences that matter, it is true that as you go infinitely far away from charges that the electric potential goes to zero. And so again, only potential differences matter. However, there is a zero electric potential, and by zero I mean that if you have two charges and this one you move infinitely far away from the other charge, well then the potential energy of that situation is zero because they're infinitely far away from each other. This is basically what this is saying. And so if things are infinitely far away from each other, or almost infinitely far away from each other, you say that the electric potential is zero, which is part of why we say that the ground is 0 volts. And the basic idea of ground is, so these wall sockets, this thing isn't providing any power in the wall socket, as many of you probably know. This thing is just there in case things get charged up. And so like this wire here might be connected to this third little prong here. And the main purpose of this is that if you have something that has if there's things that's moving that potentially create static electricity, like inside of a vacuum cleaner, you have things moving around. Might be good to plug that into things. Inside of a computer, you have things that are sort of spinning around sometimes that potentially get charged up. Well, this ground provides a way from those charges to get away from each other. And the idea of it is that, if you dump a little bit of charge on this here, because it is a conductor, those charges can move very far away. And so the reason we say it's 0 volts is because as soon as you put a charge on that, it's free to move inside of that conductor, and if there is any kind of electric field, it's going to move away from it, right? If there's any excess of negative charge, it's going to move away from that. And pretty soon it's going to be very, very far away from wherever charges that it started from, and effectively the potential energy, the electric potential, is going to be 0, and so that's why we say that ground is 0 volts. So again, I think this is most important on things where there are equipment that's actually moving around. So it depends on the equipment. You'll see some devices that just have 2 prongs, like my toaster. when I plug it into the wall, there's only 2 prongs on it. There's not a whole lot of moving parts in a toaster. So that third wire allows things to get further away. So I think I said all that. Now, because the electric field is 0 inside of conductors, it means the potential is constant. And so the potential is constant, and that constant is 0, basically. So I don't want to dwell on that too much, but I just want to introduce that concept. So that's about all we had for the day. So we're going to be doing a worksheet today that's related to accelerating particles and producing fusion and all that, trying to find the distance of closest approach. So that's what we'll be working on next. But I hope you enjoyed this lecture.